In this lecture, we're going to discuss the dot product. Before focusing solely on the dot product, I want to mention that there are a few types of vector products that we will encounter in this course. The dot product, the cross product, and the triple scalar product are going to be relevant for us. And these three products all look quite different from each other. You can tell them apart by the types of input and output, which I'm calling the signature here. So these are the operations: dot product, cross product, and triple scalar product. And the dashes would be where you would insert the vectors that you're applying the operation to. So you can see that the dot product takes in two vectors, both of dimension n, and the output is going to be a scalar, a real number. The cross product takes in two vectors, and specifically these vectors should live in three-dimensional space, and it outputs a vector that is also in three-dimensional space. The triple scalar product is a combination of these two things that takes three vectors, and because the first thing that you do in the triple scalar product is that you take the cross product, it kind of enforces that all of these vectors need to live in three space. And it returns, well, a scalar, a number. And I'm emphasizing the difference between these three operations here. So dot product takes two vectors, returns a scalar. Cross product takes two vectors, returns a vector. And triple scalar product takes three vectors and returns a scalar. So in particular, the resulting output from a dot product versus a cross product are conceptually different objects. And this kind of type checking is something that you can do when you encounter an expression. Okay. But now let's switch our focus over to the dot product solely. Okay. So this is how we define the dot product. I'm doing this in general. So if your vectors are living in an n-dimensional space, then with coordinates u1 to un and v1 to vn, then the dot product is defined as the sum of the pairwise products of the components. Right. For our course, we're going to be focused on two-dimensional space and three-dimensional space. So our vectors will live in two space and three space, which means that we only really need n equals 2 and 3, which the dot product then looks like this explicitly. And here is an example of computing dot product. So if you're given two vectors in two space, the vector 4, 5, and you want to dot it with 1, 2, you end up doing 4 times 1 plus 5 times 2, which gives you this computation. If you're given a vector 1, 4, -2, and 2, -3, 1, and you want to take the dot product, it's 1 times 2 plus 4 times -3 plus -2 times 1, which is the rest of this computation. Okay. Now we have some algebraic properties of the dot product. So each of these, I would say, is pretty important to know about, and most of them are intuitive. The first three, I would say, are fairly intuitive. The last one is something that you might need to get used to. So starting with number 1, the dot product is commutative, meaning that you can switch the order of the two inputs, and you get the same thing out. It'll be some scalar, some number. It's nice to contrast this with actually the cross product. So the cross product ends up being what we say is anti-commutative. If you switch the arguments in the cross product, you end up with the negative. And we'll see that in the next lecture. All right. So part 2 is the distributive property. The dot product distributes over vector addition. Okay. Part 3 is an associative property. So notice that in this first expression, c times u dot v, you actually have two different types of multiplications going on. You've got the dot product, and you have the scalar multiplication. And if we switch the order that we do these two operations, using the usual notion of associativity, you end up with this way of parenthesizing things, which is saying that you scale up u followed by dotting it with v. So it turns out that's the same as taking the dot product of u and v and then scaling it up, and it's the same as scaling up v instead of u and dot producting those two in that way. So we have this associative property, which is quite nice to have, kind of a thing that we would expect our vectors to do. Okay, now the last property. So if you dot a vector with itself, that's the same as taking the magnitude of the vector and squaring it. And this I thought was important enough that I actually wanted to show how you prove this result. So focusing on dimension 3 specifically, your vector v would be written in component form as v1, v2, v3. And if you just calculate out both sides of this equation, v dot v, what you do is, well, you're taking the product component-wise, and then you're adding up all these terms. And so you get v1 squared plus v2 squared plus v3 squared. On the right-hand side, you would take the magnitude of the vector v first, then you would square that. The magnitude of a vector is the distance formula, so you end up taking the square root of the components squared, summed. And you can see, which is this expression here, and you can see that these two are clearly equal to each other. Okay. Next, we have a relationship between the dot product and the angle that is formed by the two vectors. So for this, it would be convenient to do a sketch of what I'm talking about. So say that we have the vector u here and the vector v there, and that they have the angle theta between them. So we line up the vectors tail to tail, and we can see that there's an angle between these two. Well, it turns out that we can express this relationship. The dot product of the two vectors is equal to the magnitude of u times the magnitude of v times the cosine of the angle. Or if you rearrange by dividing the magnitudes over, you end up with cosine u is equal to u dot, or cosine of theta is equal to u dot v over magnitude u, magnitude v. For the derivation of this, you can see the textbook. It'll be under the proof of theorem 2.4. The derivation is kind of a bothersome amount of algebra, a bit of geometry, a bit of trigonometry. Not that elucidating, so I didn't bother with jotting it down here. I did want to remark the following, that when you solve, so a typical application is given two vectors, find the angle between the two using the formula. And so you would end up wanting to take the inverse cosine of this equation. And as you should probably be aware, taking inverse trig functions is something that you need to do with a bit of care. It can matter what the domain of the inverse trig function is, or domain or range. And but in this case, with inverse cosine, it actually works out just fine. This formula is true in general. So I mentioned this mainly to contrast it with the cross product. So in the next lecture, we'll see that there is an analogous formula involving the cross product and the angle of the two vectors. The sine of the angle between the two vectors. And in that case, taking inverse sine would be somewhat problematic depending on what quadrant your angle is in. It'll actually depend whether the angle is acute or obtuse. But here, with dot product and inverse cosine, we don't have any issues. This formula holds up. Okay. Now for an example. So suppose that you have the vector A being I plus j, and the vector B being j minus k, and that you want to measure the angle between these two vectors. So this is just applying the formula. We apply this formula that relates the dot product of the two vectors with the angle between them. So in order to plug into this formula, we need to compute the dot product, compute the magnitudes, which I've written out here. I think it's fine to follow how I did the computation. I've tried to write out the steps that one would encounter. Inserting these values into the formula, we would end up getting 1/2 as the argument inside the inverse cosine function. And then thinking about our unit circle, we can see that so this value is something that you can compute without a calculator. Not able to draw straight. So inverse cosine, as you should know, it results in outputs that are in the first or second quadrant. If we think about cosine, cosine corresponds to the x-coordinate on our unit circle. So inverse cosine of 1/2 is asking what angle does cosine return the value 1/2. So maybe you would write it like this: cosine of what angle is equal to 1/2. Perhaps with a question mark here instead. So cosine of what angle is equal to 1/2. And so as a trig problem, there would be two sets of answers. There would be the angle corresponding to this point on the unit circle and the angle corresponding to this point on the unit circle. These 2 points would have the names pi over 3 and minus pi over 3, or maybe 5 pi over 3, but I'll just call it minus pi over 3. But because we're talking about the function inverse cosine, it's specifically going to be the value pi over 3. Okay. Moving on, orthogonality. So the word orthogonal just means perpendicular. It's just a fancy way to say perpendicular. So two vectors we say are orthogonal if the angle between them is pi over 2 or 90 degrees. And we might use this perp symbol to denote that the relationship that V is perpendicular to W. Sort of a technical point is that the 0 vector we consider to be orthogonal to any other vector, to all other vectors. And the important thing about the dot product relating to orthogonality is that we can use the dot product to detect orthogonality. So if we take the dot product of two vectors and we get the result 0, that means that the two vectors that we started with are perpendicular, that they're orthogonal. I wrote kind of the rationale behind this. So starting with this, the fact that if you have two vectors and that they are not if none of them are the 0 vector. So first of all, if either of the vectors was the 0 vector, then you would have this is true and this is true, just by the assertion that I've made that the 0 vector is considered orthogonal to all other vectors. So we assume otherwise, that both of them are non-zero. Both of them are not the 0 vector. So then, well, if their dot product is 0, well, dot product is this by the by this relationship between dot product and angle. So I just replace the left-hand side, which gives me this equation. And, well, we assume that the vectors are non-zero, which means that their magnitudes are non-zero. So we can just divide by them, which then gives us this equation. Cosine of the angle is 0. And then solving for theta, we get that theta should be pi over 2. Right. So this shows that this boxed identity is true. Now let's go ahead and use this in some examples. So the first thing I wanted to show is that we can quickly form a sort of a multiplication table for the standard basis vectors. I haven't written them as a table. I've written them in a different way, but this is effectively a multiplication table. So first we notice that the standard basis vectors are mutually orthogonal to each other, right? They're all orthogonal to each other, and that's just kind of the way that the Cartesian coordinate system works. We want all of the axes to be in perpendicular directions to one another. And we also have that these basis vectors are of unit length, so they're of length 1. Okay. Then we can quickly see that that these three dot products, are all 0 because, well, they're orthogonal to one another, so the dot product is 0. And this other set is actually coming from the other property that we encountered above, which is that a vector dot itself is the same as taking the magnitude of the vector and squaring it. So that is how we can quickly see this, right? The magnitude of I, j, and k, those are all 1. And so, and of course, the 1 squared is 1. In the next example, I'm doing a more involved numerical example. So detecting whether the vector v is orthogonal to u or to w. I think it's fine to just let you read it. It's just a more practice involving computing the dot product of two vectors, just a bit of computation. And as I said, if the dot product is not 0, then the vectors are not orthogonal. If the dot product is 0, then the vectors are orthogonal. In this last example, instead of concrete vectors, like vectors with actual numbers in the components, we have these more symbolic vectors. So we can still do the dot product. Again, it's just you take the product of each of the components and you sum them together. So you end up doing x times minus y plus y times x, and those clearly cancel out. So you do get 0, which means that these two vectors are orthogonal. This actually represents rotating the vector by 90 degrees counterclockwise, if you try to sketch what this looks like. Okay. I think the last point that I want to make relating these two concepts is actually that the story goes a little bit further. So not only can we detect, using the dot product, not only can we detect whether the angle is orthogonal, whether the angle is a right angle, but we can actually classify the angle based on whether it's acute, obtuse, or a right angle. So which is the classification that I've written below. So if the dot product is a positive number, then that means that the angle is acute. If the dot product is a negative number, that means the angle is obtuse. And you can really see that by considering the following formula, right, for the angle. So in this expression, you'll notice that the magnitudes, the denominator, is always positive. So we can basically ignore that. The sign of the argument inside only depends on the dot product of the two vectors. And by thinking about how inverse cosine operates, right, it returns a result in either the first or second quadrant. And you can think about when does it return an argument? When does it return an angle in the first quadrant versus when does it return an argument in the second quadrant? And since cosine is the x-coordinate, it returns an angle in the first quadrant if what you've plugged into cosine, or if what you've plugged into inverse cosine is a positive number, right? Cosine of I'm sort of butchering the way I'm trying to say this, but so cosine of an angle is positive, means that the angle is acute. It lives in the first quadrant. Maybe I can write it like that. So in the first quadrant, and cosine of the angle is less than 0 implies that the angle is in the second quadrant. And so when we apply inverse cosine to both sides, we get this relationship. Next topic is vector projection. So consider this diagram. So we have vectors v and u. And the projection is that you line up the vectors v and u tail to tail, and you project v onto u. So that's what this notation is saying. We project v onto u. You get a vector whose direction lines up with the vector u, and its length is to be determined. So notice that geometrically, what you end up wanting to do is produce this perpendicular. In geometry, this would be called dropping a perpendicular. You drop a perpendicular from this point to u. So we have these expressions. You can use any one of these three expressions to compute the projection of v onto u, just given the vectors u and v. They emphasize different things. Notice that in this third expression, you have u over magnitude u. So this ends up being the normal vector of the normal vector in the direction of u. And so this ends up being the length of the projected vector. It's how much we scale the unit vector in the direction of u. And so this quantity is important, and it's given a name. It's called the scalar projection of v onto u, and it's denoted. You can see the expressions match. In the book, it's denoted by this comp sub uv. Okay, so I guess that the comp stands for scalar component. Now I want to kind of explain how we would get one of these formulas. So maybe before that, I want to just sort of talk through why these are all equal to each other. So first off, perhaps this one is the formula that maybe one of the first two would be the ones that you would use to actually compute the projection of two vectors. But you can clearly see that going from the first to the second, all you do is rewrite u dot u with magnitude of u squared. That's an identity that we've discussed already. And then going from the second to the third, clearly what you do is you split the magnitude squared into two different magnitudes, and you just regroup them. Notice also that the quantities that are in parentheses, these are all scalars. These are all numbers. So we're just scaling up the vector that is outside. Okay. All right, now let's come back to this derivation. So perhaps I want to zoom out a little bit so that we can see how this starts. So let me just label this by theta. Okay. So notice that we have a right triangle in this picture, and we can relate the length of this side and the length of this side of the triangle by using cosine. We know that cosine of theta is equal to the length of this side uh, divided by the length of this side. Now the lengths of these sides are going to be the magnitudes of those vectors. So that's how we start with this equation. Cosine of theta is magnitude of the projection over the magnitude of v. Rearranging, we get this equation. Next, we replace cosine of theta by this expression, which is the relationship between the angle and the dot product, as we've previously seen. And then, of course, clearing out the magnitude of v. The magnitude of v cancels, which leaves us with this. So what this computation has given us is it's given us the length of this projection vector. Right? So we already knew the direction of the projection vector, since it has to be in the direction that we project onto. We projected our vector onto the vector u, so the projection vector must be in the direction of u, and we just needed the magnitude of that vector to determine the vector completely, and we were able to produce a formula for that. So with this derivation, we would wind up with the third expression for computing the projection. And then you can easily get the other two by just winding the logic back. Okay. Now I have an example of computing the projection, the vector projection and the scalar projection, concretely with the particular examples. So if you have the vector u and the vector v, it really just amounts to plugging into the formulas. So to do the projection of u onto v, and again, like, notice that the order is going to matter a lot. If we accidentally swapped u and v in the expression, things would change a lot. So do pay attention to that. Projection of v onto u is u dot v over u dot u multiplied by u. I'm using that formula, and you can then go ahead and compute the dot products of the two vectors. And the problem asks us to do it in component form, so I'm preparing that here. And then cleaning up the computation, we wind up with the final answer. In the next part, we have computing the scalar projection. So we use the other formula, u dot v over the magnitude of u. And this is quick for us to do because a lot of the computation was done in the previous part. So u dot v we computed before. It's actually just the numerator here, so it's just 8. And magnitude of u is actually the square root of the denominator, since u dot u is magnitude of u squared. So we can just take the square root of that, and we get the square root of 13. Alternatively, I suppose you could have thought of the fact that, well, since we computed the vector projection, the scalar projection is actually the length of this vector, so you could think of this as taking the magnitude of it, but clearly that's going to be a lot more tedious to do. Okay. This is the last topic for today's lecture. So, work. In physics, work is defined to be the energy transferred to or from an object via the application of force along a displacement. You may have seen in a previous class the formula work is equal to force times displacement. Now, this is true under certain assumptions. It's true under the assumption that the force is constant and that the force is applied in the same direction of travel as the object. So for us, what matters is if we break that second assumption, if we instead have the force being applied in a different direction as the object's displacement. So suppose that you have the force being a vector, still it's a constant force, so constant vector, and displacement you can also treat it as a vector, which I'm denoting by S. Work then ends up being defined as the dot product of the two vectors. And this equality is just using the relationship between dot product and angle. Right? The dot product of the two is equal to the product of the magnitudes times cosine of the angle. So we then just use this formula in the following example. So in this example, the wagon is being pulled with a force of 8 pounds at an angle of 55 degrees. And the wagon is displaced by 50 feet. To find the work that is done by this force, you would just apply this formula. So magnitude of the force vector times the magnitude of the displacement vector times the cosine of the angle between the two. And you would just go ahead and compute that. To calculate cosine of 55 degrees, you are forced to use a calculator. So I did that and I got this answer. And the units for this type of problem should be in. Typically, you'll see work either has units of foot-pounds or Newton meters, aka joules. It depends on what unit system you're using for the problem, so just be aware to check that. And that's all I have for this lecture.